NEA कुरा हामी लिएर आइरहेका छौँ। सन्दर्भमा आजको हाम्रो टपिक रहेको छ Engineering the Future Power Grid with Distributed Energy Resources and Intelligent Energy Management System on the Smart Grid भनेर। र आजको हाम्रो स्पिकर इन्जिनियर पारस मण्डल, उहाँले विषयमा कार्यरत हुनुहुन्छ। अहिले आफ्नो बारेमा थोरै भनिदिनुहुन्छ होला र यस प्रोग्रामलाई अमूल सुरु गरिदिनु स्पेलिएर प्रेसिडेन्ट हजार शिक्षकहरुमा आग्रह गर्न चाहन्छु। यो सबै हामीले यस प्रोग्राम दुई सेसन हामीले बाँडेको छौँ। पहिलो सेसन भनेको स्पिकरले आफ्नो ट्रेनिङ स्टाइलहरू चाहिँ प्रेजेन्ट गर्नुहुन्छ र दोस्रो सेसनमा यहाँ के सजेसन क्वेरिज पेजहरू त्यस्तो उहाँले राख्नुहुन्छ होला। र अब हामी जान यो पारसहरुमा आग्रह गर्न चाहन्छु।
Thank you, Ravi. So the title of my presentation is basically I'm going to talk about what is smart grid. I'm going to focus more on about power and energy systems today. So my name is Er.Paras Mandal, and right now I'm an assistant professor of electrical engineering at the University of Texas El Paso. It's a southwest corner at the US, close to Mexican border. And so my presentation is I'm going to give you a very brief introduction about myself and some basic concepts about smart grid and some research simulation results on power system forecasting problems. Specifically, I'm going to show some results on electricity load forecasting, solar power and wind power forecasting, and some mechanism of energy storage system followed by response as demand side management. And I'm going to put some concept about microgrid, and a new concept on transitive systems. So basically, very brief introduction about myself. I have electrical and electronics engineering from India. Then I went to Thailand for my master's degree in electronics and planning. Then I moved there for my PhD in power system, which I finished in 2005, September, I believe. And that's my education background. And I moved to, then I did my first postdoc in Japan itself. And I moved to South Korea, Seoul as a research professor. And further down to South Korea as a research fellow. I worked there almost 2 years. Then I moved to Calgary, Canada, and another part of Canada as a postdoc again. And finally, I landed up in Texas as a tenure track assistant professor. And so far, I'm a student at the moment. Very brief background. So, at the University of Texas at El Paso, I'm the director of Power and Renewable Energy Systems Laboratory, and it is known as PRESS Lab. Basically, in my research lab, we work in different aspects of power systems with more focus on market, power planning and operation. And I work a lot in computational intelligence systems like neural network, fuzzy logic, etc., particularly in power system application. And we work very deeply in renewable energy system, primarily wind and solar. And this is the area that we started growing up in this area: distributed generation, predictive algorithm, uncertainty modeling. Because in power system there are lots of uncertainty, how to handle the uncertainty. One of my areas at this moment, and I mean my students are working in that area, and definitely intelligent system applications. Of course, in addition to these research activities, we work purely on engineering education also, because we need to encourage our community of female students more on engineering degree in power system or etc. So engineering education is also one of my educational activities over there. So in my lab, we work in microgrid energy. At this moment, we are working on microgrid energy system and smart distribution systems. And this is a new concept. I'm going to talk about this guy a little bit towards the end of the presentation on effective energy. And we work in cyber security, lots of cyber threats going on, attacks going on. That's another research area that the research group is working on. And energy forecasting, optimization, supply chain management is the area we are working on at this moment. So whenever we come across with the term power system, some of the important terms that we come across are reliability of the system, security of the system, resiliency of the system, sustainability, pricing, electricity price plays very important in the power system, and efficiency. But however, there are several issues like vulnerability, blackout, etc. So we need to come up with several intelligent model or very highly sophisticated system in order to handle those issues in the power system. So basically, power system is what? Just follow basic principle of economics. That means supply should meet demand second to second basis. Like for example, if I want to turn on the light, I want the light to be on. I want it to be off. I don't want it to be in this situation off and on. So in 2003, in summer of 2003 in Northeast, around New York, Ontario, Canada region, there was a huge blackout, and almost 50 million people were impacted. Some were washing their car, some were withdrawing money from ATM. There were several laborers and pains in hospital. Many people were impacted, and that was really a very important event in power system, and that has become a very important lesson for all power system engineers, all the energy engineers, all the energy economics policy makers. So, how we drive? What is the main driving factor for future power grid? It is nothing but recent blackouts, aging infrastructure, blackouts. We are highly impacted by energy emissions. How to lower down the carbon footprints, etc. There are several factors that is making us very intelligent and sustainable future power grid. So I'm going to talk about that with focus on smart grid today. So power system is nothing new. Edison in 18th century, he actually established a very small power system in New York with 59 consumers who were utilizing the power. Very simple, it's a generator, cable, and fuel and electric lamps. And it was, I believe, 60 hertz and 110 volt over there. So power system is nothing new, but it's an evolving, it's growing, it's expanding. Lots of things are coming up in every this and next years. So I always mention that power system is one of the most complex human-made systems in the world. I highly emphasize that power system is highly complex. So this is what's happening as a power flows from generation, via transmission, distribution, and we are the consumer. We are consuming the loads here. This projector is consuming load. This is simple residential load, not commercial building load. So that is the basic flow of power from generation towards consumer, and we are the customers here. However, in smart grid, the main objective here is how can we improve the resiliency of the system, efficiency of the system. How can we make our system more secure? So that's the advantage, that's the main objective or goal of smart grid. If you see here, power is flowing here from generation to customer, but in smart grid, there is a power flow there is information flowing from consumers to generation or other side of it. It's a two-way communication. So that new thing here is smart grid, which differs it from a traditional power system. That means traditionally there was side driven, and here we have a two-way communication. The information is flowing, power is flowing, and we know what is going on in the system. And more importantly, we have electric vehicles, wind, solar, energy storage devices. These all devices, all resources are coming into the system. And to be noted that the most important thing as I have underlined here, in smart grid operations, there is an active participation of customers. We want consumers like you, I, to involve in the system. Because ultimately the main goal in the system is we consumers should be happy. We want to consume the power, but with minimum price. That's the theory. I want to go and purchase some shoes outside. I want to get the best shoes at cheaper price. This is every consumer. I want to fly from here to Viratnagar or Janakpur. If I want a ticket, I want to check which airlines will give me the cheapest price. I will fly in that airline, right? Because we want everything perfect but the cheapest price. So this is the picture I adapted from this website. If you notice here, we have wind turbines, wind farms, we have commercial buildings, we have solar panels, smart appliances, demand side management happening over there. We have microgrid. I'll talk about microgrid later on. So we have industrial sector. We have several things, but they are each other are connected. They are connected. They are automated. The consumers are active there. The producers are active there. The system is highly automated here. So today I'm going to talk about, not all because of lack of time, I'm going to talk about wind power, I'm going to talk about solar power, I'm going to talk about demand management, demand side management, in particular I'm going to talk about demand power and microgrid. So let's start with a very simple smart grid. So traditionally what used to happen is, if I am a producer, if I am a generator, I used to just generate power and just anticipating that customers are meeting the demand. There is very simple forecasting method over there. But right now in smart grid paradigm, we are much more focused. We are much more emphasizing on how to make the system more reliable, interactive, interoperable, secure. So that is the main major elements of smart grid. So in smart grid right now, in today's grid, what's going to happen is we have lots of distributed energy sources. For example, wind, solar, electric vehicles. We have distributed generation, fuel cell, energy storage, battery energy storage, etc. At the same time, energy efficiency initiatives are being provided here. I'll talk about the initiatives later on. And more importantly, advanced communication system. Because lots of cyber attacks going on around the world, and power system is one of the main targets. Because everything has been computerized these days. Lots of intelligent algorithms are being developed. So cyber attack and cyber security issues are, because of those things, smart grid is also playing an important role, how to prevent our system, how to make our system more healthier. So some issues in smart grid planning and operation. This is a very simple wind farm, and we get when wind blows, wind turbine will generate electric power, and which has to be included into power grid. But issues in wind power output is output power is highly variable, because if wind blows, wind power will be generated. If not, there is no use of that. And usually wind turbine blows much during night time compared to daytime. And look at this graph. This green is nothing but wind power. This depends on this blue curve, which is wind speed. And these signals are highly intermittent. It's highly stochastic. I term it as very non-stationary. It's because this wind power purely depends on weather. Similarly, solar is purely dependent on solar radiation. If there is solar radiation, then the solar panel can give you the output. And again, the output of solar power output is very, very variable. It's not stationary. It is totally different from load demand, where we can expect that from Monday to Friday we have some particular pattern of load demand, and in weekend, Saturday and Sunday, we have similar pattern, but the load is little lower than load compared to day. So, as a power system operator, all power system operators, they are having very, very challenging issues because of high penetration of wind, solar, and because of rapid growth in technology. That always there is an advancement going on. Because of this, the forecasting optimization has become much more complex. Please note that in power system, along with many other engineering disciplines, it involves lots of optimizing problem. We have to optimize several things. Like for example, there could be many lights here, and Rogis is just around 6 or 7 lights. We want to optimize the light, but at the same time give the correct output in the room. So we have to do optimization in power system. So reliability and security is other issues. And in the energy market, there are different market pairs: aggregator, producer, generator, distribution companies, transmission companies, etc. So this makes the system much more complex. And accordingly, day-ahead planning is what's going to happen tomorrow or next several hours, next week. This will become much more complex. So I'm going to show some results on based on my past research on electricity load forecasting, electricity price forecasting, wind power forecasting, and so on. So I developed a method called similar days method. Actually, what it does is, let's say it's 4 p.m. today, 16th of June, Friday. I'm going to forecast 5 p.m., 6 p.m., 7 p.m., 8 p.m., and let's say until tomorrow, the next 24 hours. So based on this principle, it gathers all the similar information from the past, from the historical data. For example, it is June, so I'll ask my algorithm, hey, go back minus 30 days or minus 45 days from today. And last year, June 16, again go back minus 30 or 40 days whatsoever, minus and plus. So I have one equation over here, and that equation will give me the load demand what will be the very similar to today's load demand, which is going to be the next forecast load. So that is similar days method gathers the historical similar information corresponding to forecasting hour. So that will be the similar day forecast. But this is just a naive approach. I'm going to use this forecast as the first step into my neural network or any other forecasting model as for further forecasting. I'm going to show how it's going to happen. However, I was writing one article on this, and reviewers were asking me if we do not find similar days. Then I developed another algorithm, like because temperature varies, the weather is not in our hand, it keeps on varying, and accordingly there could be shortage in similar days. So what I did is, because of that, the load forecasting is going to be very tough. So I developed one method called load correction method. What it does is, any old historical load data will be multiplied by load correction rate. I didn't show any mathematical formulas here, but you can see transaction journal paper. So I multiplied that historical data with load correction rate, and this involves some regression, some statistical modeling, and I'm going to get the new similar data. So for that, what I did is the upper end of the load demand. I enter with the maximum temperature and lower with the lower minimum temperature. And I developed new equation called this equation. Actually, this is nothing but based on Euclidean norm. Euclidean norm means in the space we have several data, and we want to classify the data which have similar properties. So that Euclidean norm gives me that. So this equation will give me new similar data, and I'm going to use that data into a forecasting model for further forecasting process. So this is nothing but the original load data, and this is the correction data. So this equation is giving me further analysis on better forecasting. Because temperature is not in my hand. Like all of you, when I was coming here, I didn't know, for example. So that I wasn't expecting. I didn't see the weather forecast today. So that makes the weather quite cooler compared to previous tomorrow. So the weather really impacts the load demand. And what I did is I forecasted my load with similar days method and fed it into a neural network. So this is a very simple feed-forward neural network, and it is an intelligent model. neural network. I'm not going to talk about neural network here, but it's an intelligent model, and it really deals with the nonlinear data. It gives a good relationship between input and forecast very well. So what I did is I forecasted using similar days method, and I fed the data here, and it is being trained, and my neural network model will give me the forecast output for next several hours. So, however, what I did is I further developed another model, hybrid intelligent model, and I use it term as hybrid neural fuzzy. So neural network being combined with fuzzy logic, and I was testing if I had a better output. So what I did is I tested in three different seasons. One is special days, typhoon or hurricane time, any national holidays, ordinary days. Like today is ordinary day. And if the humidity, comfortness is below or average or etc. And another one is precipitation. If there is rainfall or not, I tested an algorithm different weather conditions. So this was done first. Then I improved the output using neural network. The output came here, and I applied this output and fed here in the fuzzy logic another intelligent model, and I got the forecasted load, which is the final. And I'm going to show what is the forecast error. It was tested in Japan in Okinawa Electric Power Company. This model was tested. It was working well that time. So my error, just using similar day method, was 4.7%. Only using neural it was 2.24%. That is mean absolute percentage error. And after combining neural network with fuzzy and including similar days, my forecast and load forecast error fell down drastically to 1.71. Actually, to let you know that load forecasting is one of the very important steps in power system for any progress, and the error up to 2%, 1.5% is going very good. But we hardly get this kind of errors in wind, solar, or electricity price. And the major contribution of this paper was able to reduce the forecast error by 23%. And this work has been published in IEEE transaction on power systems journal. Furthermore, I tested my load forecasting with another intelligent model with fuzzy Er.Paras. This is not similar to fuzzy logic. Another fuzzy Er.Paras. I optimized this model using optimization algorithm called Firefly optimization algorithm, and I considered dry bulb temperature, dew point temperature, and more importantly, in a smart environment, I considered the price, because price also will play an important role in load. And I came out that I tested this in US and for different period of the year, New Year Day, Martin Luther King Day, Memorial Day, Independence Day, Labor Day, etc., including Christmas. And I was able to get forecast error ranging from 1.5 up to 3% here. So this paper was also published in one of the journals called Procedural Computer Science. Okay. Furthermore, I continued working on forecasting but electricity price because in the energy market price plays a very important role. So I was able to get the LMP means location marginal price is a price for a particular location. For example, Java-Cal has one price, Hypertele has another price, maybe Manila has another price. So location-wise the price will be different. So that is LMP. So I will get for high demand week. This is the electricity market in the US. High demand week that time was almost 40,000 megawatt for that particular day. I believe it was in February, sorry, in July probably. So that time the price was quite high. The error was giving me quite higher error. This is the forecasting of the price for the whole next next 168 hours and for the next 1 week. And I further tested my algorithm with price forecasting, and I was able to get the error with 3.6%. And this was an IEEE transaction in Industrial Application Society, and I was the recipient of the best paper award for this work. You can easily access this paper from IEEE Explorer. So next, very briefly about wind power and solar power. Wind power forecasting is very challenging. It's not as easy as computer load because of the intermittency of the wind speed, variable power output, But we were able to do a good job in wind power also, forecasting around 10%. But we did two kinds of forecasting. One is point, another is probabilistic. We use fuzzy arithmetic, we use machine learning like support vector machine, and it was doing a good job on that. But recently, one of our students did a good job on very short-term wind power forecasting. We introduced emotional neural network. That is the first work, based on my understanding, that emotional neural network has been applied for any wind power forecasting area. We got a very good result, and we utilized the wind farm data of Texas and I'm going to show how the errors look like. We tested for different seasons of the year, summer, fall, winter, and spring. And we tested with benchmark persistence method. And we use different methods, singular day, back propagation neural network, regressive function neural network, generalized regressive neural network, emotional neural network, and different hybrid algorithms. And we were able to get the forecast error up to 7%, ranging from 3 to 7%. It was quite a good error for 10 minutes forecasting from, let's say if I'm at 5 p.m. now, I'm forecasting 5:10, 5:20, 5:30, 5:40, 5:56, and this was done probably up to next 6 hours. So very short-term forecast is very, very important for power system scheduling, specifically for generation scheduling, unit commitment, economic impacts. This is very, very important in system planning. It was actually in one of the conferences in Dallas in IEEE annual meeting at Industrial Application Society. And for my students are also working on probabilistic solar PV photovoltaic power forecast. So this is the probabilistic means instead of, let's say if we can check in website the temperature in Kathmandu could be around in Celsius, it could be, what is the temperature now? 29. Okay. Let's say 6 p.m. is now 28. And I'm forecasting, and my forecast model will give me 20.5. So I have a difference of 0.5, right? So, but in power system, that is the point forecast, 20 to 28.5. But in power system, we are much more concerned about, in addition to point forecast, probabilistic. How about the forecast that goes from 26 up to 29.5, or maybe 26 to 32? So accordingly, power system operator can have a very good decision for which plant to be shut down, or which unit could be committed or deleted. So that range of error will help the system operator to have a very near plan. So that is another important work when you implement that. So bottom line here is, this was traditionally weather was a parameter, time of the day, different distribution system used to be the input parameters in the forecasting model. However, in this smart grid paradigm, we have to use market price, electric vehicles, different wind and solar storage devices, and to make this forecasting much more accurate. So that is load forecasting in smart grid era. This is about my forecasting world. I have quite a considerable amount of publication in power system forecasting. You can Google also, and also receive Best Paper Award, not only IEEE, others also. And I have a book chapter in IEEE actually is going to be published very soon, just as I accepted. This is about forecasting world. I'm going to talk about, okay, let's have some break. So how many of you are a student here? Okay. So how do you analyze this stuff? How do you read it? No, I'm asking him. How do you analyze this cup of water? Okay, you.
Analyze in two different ways. One, it is considered it is half filled, or you can see another way it is half not filled or half filled. Right?
Okay, that means either we can be optimistic or we can be pessimistic, right? But we are engineers. That everybody we can analyze that. But engineers we analyze in different ways. To the engineer, the glass is as big as it needs to be. we are different. Right? So we think differently. And another humor is very normal people believe that if it isn't blocked, don't fix it. Engineers believe that if it isn't blocked, it doesn't have any fixes yet. Okay, so now I'm going to talk about distributed energy resources management. So ultimately, the goal of any system, civil infrastructure, construction management, bridge, highway, power system, airport, any system, anything that is functioning is called system. Any system, it has to be managed very well. That's why we have a maintainer. So I'm going to talk about what is energy storage system, demand response, microgrid, transit-driven system, and I'm going to come on my own forecasting everything there. I'll make a small intelligent system now, and how to manage that system intelligently. So just look at these two figures. So I just explained about forecasting of wind power, solar, load, etc. Right? So what is the definition of forecasting? Forecasting means everything gonna happen something in future, but there is always an error. That is forecasting, right? So there is an error in forecasting. Nobody can forecast anything with 0% error. Nobody. There will be at 0.5, 0.1, depending on which domain you are working on. I already showed how much percentage going on. So what actually happens is what exactly energy storage do is I'm gonna integrate a storage system into my let's say grid or in any microgrid, etc. I forecast the power just now. I'm gonna utilize the energy storage to forecast with the actual one. I had a forecasting of 28.5, whereas the temperature was 28. So I will hook energy storage device there. I will try to make the forecasting very close to actual. So that is called leveling of the actual with the forecasting. So that is the one of the word we are working in my lab. So you can see that energy storage system can keep the level value within 1 to 5%. So that means if I have 0.5, so I can come up with 20.2. So for example, let's say if the forecast value is 1 megawatt, but actual value is 1.3 megawatt. So it's a difference of 0.3, right? So what does energy storage will do is he will absorb 0 megawatt and store it. And when needed in time, it can be supplied by power grid. That is uses resources here. Actually, one of my PhD students, he presented this work in one of the IEEE conferences in Charlotte, North Carolina. So, this activity that we do in my lab is we forecast wind, power, solar, etc., and wind commitment problem. How many of you are electrical? You're probably studying this in our system, right? Yeah. So this is good commitment. Then we'll forecast in real-time management. Real-time I will consider as a very close to 5 minutes. 5 minutes from now. I don't want to change my algorithm after that. I don't want to start my system. So when it is forecasted, maybe 6 hours, 1 day ahead, then I'm going to forecast very time. Then I update the system. For example, the load demand in Kathmandu is, let's say, 300 megawatt. The whole country is 600, right? So I was in 250, let's say. So let's say we have a system of wind and solar, and wind and solar is contributing 50 megawatt, let's say. So that 350 minus 50, 300 is the net load, because wind and solar are considered as negative load. So that is the contribution of renewable sources. So that has been updated into my algorithm, and we further go with this and we just spare units. Okay, demand response program into a smart grid operations. Have you heard of demand response? Anyone? Demand response.
Demand response means labeling the loads, shifting the peak hours.
Very, very important point. Exactly. So this graph exactly is explained. So this is one of the examples from your city market. We call your Indian system operator NEA. So look at here. The blue curve was hitting 35,000 megawatt. Okay, and when demand response, mechanism of demand side management. So when demand response program was introduced, the load for a particular time reduced from 5,000 megawatt. That's a huge load, and that load, some residential consumers or commercial, some even incentive on that. Right? You do not have the load from 3 to 4 p.m. and you will be given incentive in your next electricity bill. Maybe some dollars. Okay, and they will sit and wait. Similarly, like I'm gonna wash my clothes in my washing machine at 5 p.m. and I see the electricity price is quite high at the time, but I will say, oh, this is quite higher than other time. I'm gonna defer the time, maybe next hour, maybe after at 9 p.m., maybe 10 p.m. That is shifting the. In fact, when the new regulator came in NEA, Nepal Authority, he's not doing demand response, the demand side management, shifting the load from peak time to other time. So, but without compromising the system's adequacy, quality, and reliability. It is just shifting, like I might be having breakfast at 8 o'clock, but due to this thing, I might be switching to 7 or 8:05. So that is called, but I'm still managing hunger. So demand response is why bringing this terminology in key characteristics of smart grid. Very, very important. Is the sharing or shifting of the load or reducing the peak hour load. Ultimate goal is nothing but how to enhance the efficiency of the system, how to enhance the reliability of the system. So all this, the examples of demand response. This is V2G. Everyone knows V2G. Anybody? It's a vehicle to grid, exactly. So in this research, what we did is we have electric vehicles, we have battery energy storage system, we have solar here, and this is a small system but connected to our grid with PCC, right? So if you see here, what we did is the output of solar power is fluctuating. So what we did is we connected this with the battery and electric vehicles. And here electric vehicles and battery, there is a battery inside the vehicle, right? It needs to charge, and to operate it will discharge, right? Certain kilos depending on what the capacity of the battery. So here what we did is we considered this amount of battery for the electric vehicle as a demand response mechanism here. And it was working good, and we did a very good optimization here using genetic algorithm, and we calculated some cost and benefit analysis there, and we actually published a paper in International Journal of Sustainable Energy. So that was one simple applications of demand response to electric vehicles with vehicle to a grid. Sorry for the clarity of the picture here, it's not much clear. Just very simple, what I'm going to explain here is we have this building, we have other buildings, UN building there, and another building, we have a number of buildings here. So every building have different kind of loads, right? Like the way I use the load consumption will be different from him, from you. So we have this different how to manage and how to have a good way of management of buildings. So we come with distribution system level robust optimization. So we have several buildings here. We forecasted load, and we introduced some renewable electric power there, and everything has been aggregated. The price factor here, and finally dispatch the system. And this was one of the very well-cited works going on in my field. Many researchers from the world are citing this work. and published in this Renewable and Sustainable Energy Reviews journal for the smart distribution system. How can we make the distribution system more smarter? So that is one of the work here about smart distribution systems. Coming to the almost towards the end of my presentation, little bit, maybe a few more slides. Microgrid, which is another distribution system. How many of you know what microgrid? Anyone?
Because of this small sources within the small area and be supplied by that source or something.
Okay, for example, if this, let's consider this building is a small city or small, just or F910, and we can have different sources there to sustain ourselves. I mean, it can work in connected mode with the NEA grid, or it can work in disconnected mode, which is termed as islanded mode. I'm going to talk about that a little bit later on. So basically, the simple architecture of microgrid. You have fuel cell, as you mentioned, you have there could be different sources. Like there could be wind, there could be solar only, there could be hybrid wind and solar, storage devices, you have thermal load, and ultimately this guy has to be connected to the power grid. Because if they have a surplus energy, we will sell energy to NEA, and we get money on that. That is called energy trading. So microgrid is nothing but it's small, independent, and it's a decentralized system. So Department of Energy further defined microgrid as interconnected loads and distributed resources of energy. We can clearly define boundaries. Boundaries means some boundary. Maybe Java area could be one boundary, Java area could be another boundary, Neural area could be another boundary. Okay, so very interesting. This picture is actually from California, and this is a jail. This is a prison. In prison, they have implemented a microgrid. They have tested successfully. You can see you have 1.2 megawatt of 2 diesel generators. You have very intelligent distributed energy resource management system. They have 1 megawatt of fuel cell, that is the energy storage system. 2 megawatt of advanced energy storage system. They have rooftop solar also on the top of the jail. They have wind turbine somewhere far with 2.3 kilowatt wind turbine. And this has actually tested, and this is a very good initiative or good work done by the Department. So that is very interesting microgrid here. So if anything happens, these guys will always have electric power. They have their own sources of energy. They don't have to rely on the grid. And none of the prisoners can run away. Okay, so far I've been talking about forecasting, microgrid, demand side management, demand response, renewable electric power, wind, solar, etc., etc. So my vision actually for Nepal's future power grid may happen sooner or later, but it will happen in next time. Sometimes I don't know when. So my vision is how can we have multiple microgrids, and for that, how the new approach, the new concept called transactive energy can be implemented here. Let's assume that we have residential microgrid, commercial. Residential means the way where we scale, right? Residential building, commercial building, and industrial. We have n number of microgrids. And how demand prices of electricity can play an important role in managing the microgrid. And I'm going to end the presentation. So please note that this is my vision of integrated framework of energy management system, where I have just mentioned some forecasting system, storage system. This is the distributed system of it. Like in Nepal with Pradikaran, we have transmission sector, distributed sector. It's a centralized system, right? Whole country is the same guy. The head office is here, right? It's a totally centralized system. If something happens somewhere, there will be backup. And I think the system is highly vulnerable. So how about if we decentralize the system? So for that there is a new terminology called transactive energy. It is exactly, it's not same as smart grid. There is a little bit different between transactive energy and smart grid. Smart grid has lots of data flow. Maybe every second, every second. That it contains a lot of data. In transactive energy, what it does is it uses the data, collects it very wisely, and implements to the implementation for resource allocation, ancillary services like voltage regulation, frequency regulation, load management, and etc. Lot of things. But most importantly, transactive energy's main concept is it gives us two important signals: economic signals and control signals. We're talking about megawatt, kilowatt, megawatt, what is the control signal, but what is the price for that? That's very important. So, transactive energy is a multi-agent system. We have lots of agents here, like producers, generators, transmission companies, aggregator, broker, etc. So the main objective is how to maximize the benefit of the system at the same time increase the reliability of the system. So I'll show you one picture here. Look at this simple microgrid. Microgrid 1, we have substation, we have load, another microgrid here, another microgrid here, we have like that. These two signals is called transactive incentive signals and transactive feedback signals. That means how much demand you give me, I'm going to charge for that demand. So this price and demand will flow continuously every hour or every 5 minutes depending on the time interval. I can do 10 minutes, 20 minutes, 30 minutes. In very similar way, every hour I'm going to demand the price, keep on varying. So what is the benefit? The benefit is that it's a forward signal and it will help us to minimize the load at the same time maximize the consumption. We want to maximize everything. I want to charge the cell phone at the same time. I want to play the music. I want to watch television. I want to iron my clothes at the same time. But I have to pay for that. And what is the optimal price for that? So, transactive energy, multi-microgrid, and interfacing distribution system with transmission system. So, in this figure, let us assume that this is whole Kathmandu. This is our hill, microgrid 1. And this is Chavale covers, let's say Chavale with the Barbarsala. And you have other microgrid in, let's say, Kuleshwar area, goes up to Thapatali and Javalakhe, etc. Let's say let's say 5 microgrids in Kathmandu. So, I'm the microgrid controller of my area. He is from Chavale, he is from Thapatali, he is from Javalakhe. So, every microgrid has one management box. It's called microgrid control. But we all microgrid controller are working under the umbrella of distribution system. This is the main boss. Anything gonna happen under this umbrella is his responsibility. His main job is to maintain the reliability system, to enhance the system, and really all that. So what he does is, hey guys, why don't you sustain yourself? If anything happens, I will take care of that. That means if there is some shortage of solar power, wind, or anything, you will have to use the thermal sources from far end, maybe from or hydro, whatever. You will manage that. So I have, let's say, battery here. I have wind, I have solar, or maybe I have just wind. So my demand at this time is 500 megawatt, 200 megawatt, and I'm generating 175. So and you will say, oh, these guys at this time 5 p.m. they are lacking 25 megawatts. So what this distribution, the system is highly automated. What he does is, oh, this guy is generating 15 megawatts surplus energy, and this guy is generating 5 megawatts surplus energy. So what he does is that surplus energy will be supplied to this guy, but he doesn't know where he is receiving from because the system is receiving from the feeder. But this guy who supplied 10 megawatt surplus, other guy who supplied 5 megawatt surplus energy, they will receive incentive. So that is called energy trade within the same market. But how about we within Kathmandu, we are having efficiency of 100 megawatt. However, in other region, Pokhara region, in Hetera region, they are having surplus energy. So this is a transactive coordinating system Kathmandu. This is transactive coordinating system Pokhara, transactive coordinating system Nepal. So we can do energy trading not within the same city, but neighboring coordinating system also. So this is a multi-microgrid energy management system where this is, I just brought a very simple with a lot of mathematics, lots of mathematical equations I didn't bring here just for the simplicity purpose. But very, very interesting work going on actually in the other side of the country, in my research group as well. So energy trading. I mean, you eat yours. If I'm hungry, I'm not gonna give food to you. I'll eat first myself, right? If I have some surplus food, then I will distribute. But give me money on that. Then I have to there are lots of maintenance costs on the machine, operation cost of the machine. There are lots of staff working. I have to pay the second of that, right? So that is called energy trading within or neighboring cities or whatsoever. I can also do energy trading from this building to that building. Let's say I'm in vacation from for example. The consumption in my house in Texas is very low. So I need that have surplus energy, and it can be supplied back to grid or to neighboring buildings. So I believe my vision for this, why I'm bringing this here, is we are better shape than before. The load shedding has gone down drastically, at least half of the time. But we are highly hydro dominated country, not to be forgotten. So our hydro, please note that we have 55,000 megawatt of hydro power potential in this country. Country of 30 million people, I believe. But economically, we can exploit 40,000 megawatt. Bhutan already exploited around 10,000 at least, and the population of country is just 720,000. Very countable population. So our hydro power policy can be easily integrated to our microgrid system, distributed system, and it can be exported to India also. We don't need it. We can easily export. We have lots of border with Nepal, Roxol, money in this area. We can easily export it to northern side. So bottom line is let us fulfill our stores. Then give our close friends. And his stomach is again, if he is still full, give to the city. It's still full, give to the other country, neighboring country. And I'm pretty sure one of our incomes of our country is tourism, but energy sector is really will play an important role. We can really be a very good example. Like Bhutan is giving a good example. They have always surplus power most of the time, 99%, but the generated power, extra power to India, right? Cheap price. So we can have a very good energy policy. We can do better job in very near future. So summary. Forward energy forecasting tools, price is a very important signal. We can do lots of, we can create business electricity within cities, within the country, and neighboring country also. It's a business. You just generate, you eat, then let others eat. So these are my main summary. Do energy trading, bring microgrid, bring more renewable. Of course, hydro is our main source of energy, right? So I have different project grants going on. So some of them are pending. Some of the grants we have with are shown here. So at the end, thank you very much. And the lady, if you read a cartoon there, in electricity market, when it is deregulated means when there is competition, we have different source of supply. Consumers can have choice of buying power. substitution into any supplier. So I believe we'll have such future. So that I want that like here. This is one of the internet company. Maybe there are n number of internet companies. So we have choices to choose which internet we want from, right? So maybe in the future we have similar ways of choosing our product. Any questions? Thank you very much.
Thank you, Pastor. यो यहाँको के कमेन्ट सजेसन केही छ भने आफ्नो पछि दिएर गर्नलाई मन राख्दिनु।
Thank you very much for very good presentation and experience sharing. There are several questions. Should I ask one by one or okay? So first thing you have shared the day-ahead electricity market and week electricity market. I think these are good concepts. Deregulated electricity and in Nepal, we are not in the situation of deregulated electricity market because still we are in response to the demand situation. We don't have surplus of energy. So in this case, do you have any some rule suggestion that we can do energy planning? Like for the Kathmandu city, I can have per kilometer square of 10 megawatt or something. Some rule for the developing city like Kathmandu or other. If any experience, please share that. And another is like you have also mentioned, we have several cross-border lines with India. So India have several, I think more than 28 SLDCs, state LDCs. So we have connected with the HVAC, with the cross-border line. So Nepal INPS, it would be like integrated Nepal power system. I mean Nepal power system. So will it be like SLDC of India? I mean the frequency control and all those things are giving it to the India. It shouldn't be like back-to-back HVDC connection so that we will have independent frequency control both sides. So like US and Canada border have back-to-back HVDC connections. So what is your opinion on that? So especially for the policy makers, it is very. And another is a smart grid like communication systems. I think the generation side and transmission side. Even I can say the INPS is smart enough. So challenge is the distribution, communication distribution side. Like I mentioned that, like in my home, I have the free PV and all appliances. I should have planned like my refrigerator should on the off-peak hour or maybe the least price time, or maybe the least priority equipment should be on during the off-peak hour. So this requires again the communication. I heard that CCN and all are working on this communication system. Still it's challenge. So will it be challenge for the country like us also? What is the experience of USA? They achieve this communication in the distribution and two-way communication between the utility and the household. Yeah,
okay.
Put
So,
three questions. Yeah.
your first question is forecasting. The second question is
cross-border transmission line frequency.
third question is about
Communication in the distribution.
So actually, the forecasting here, I don't know what algorithm Nepal Electricity Authority they use. I don't know. Forecasting is a lot easier here because demand of this country is of our country is what 70 megawatt. It's under 800, right?
951 now.
Right now?
Yeah.
950.
Yeah. 950.
But how much generation capacity we have?
You mean?
What is the install capacity?
Hydro is 953 installed capacity.
That? Okay, so actually forecasting here can be done very smoothly because we don't have much in here in the country. We are very countable, right? Compared to other countries, and we can easily have industrial load we have usually have commercial load, we can have residential load. So the maximum demand will be in Kathmandu compared to other cities, right? So if you just focus on Kathmandu and develop an intelligent algorithm on that, that same model can be implemented to Western Far Eastern and Western. Use temperature. And in Kathmandu, the humidity is very less compared to Nepal. Add humidity factor in forecast model in Nepal. In Pokhara, maybe similar to Kathmandu, I believe. And Pokhara has more rainfall compared to Nepal, right? I showed that different conditions, rainy conditions, humidity conditions, etc. Right? So these factors has to be considered into forecasting model as inputs, and accordingly we will forecast demand. And we can forecast demand for next 30 minutes, next 1 hour, the next 6 hours, next 24 hours, and accordingly for next 1 week. Because we can do very short term, means 5 minutes ahead until 30 minute usage. Short term load forecast is from 1 hour ahead until 24 hours ahead, and medium term up to a month or etc. So we can do very short term, medium term, and long term planning. The long term planning is tough because you have to have different forecasting input parameters like GDP, GNP, some economic parameters. So the forecasting department of NEA should consider these factors for the very short, medium, long term. And I tell you, I can give them my algorithm, I can test. I can give them very good forecast. Going back to your stuff, what I'm trying to say is that you eat first, then give the stuff food to your neighborhood. If they are still not hungry, give to the other city. Then only race up to India. To meet our local demand first. Right? What is the theory of economics? The supply should meet demand second to second basis. Right? So that frequency and voltage ranges, these are all ancillary services. So when energy trading will be done, when there will be mutual agreement, the regulator will take care of that from both parties. So we have to maintain 50 hertz, 50 hertz here, right? 50 hertz with some plus minus here and voltage level. And HVDC is okay because if you are supplying large blocks of power, HVDC will be there. In Canada and US is why? Because Canada has huge amount of hydropower, right? They have large, and there is a good connection of HVDC, so that surplus energy can be easily exported or energy can be exchanged to Buffalo area actually. So that could not be an issue. That is a secondary tertiary thing. The first thing is energy trading, and for the energy policy should be there. Going back to your third and very important, very interesting question about distribution system. Distribution system is the most challenging sector now compared to generation transmission. We have everything challenging, but distribution because we consumers have different activities. We have our activities are varying, right? And accordingly, the distribution system operators, their load modeling should be carried out accordingly. So appliances could be one thing because we have residential sector, commercial, industrial. So the load behavior or load profile of this sector can be easily studied well. In general, like in US, common appliances in a home will be microwave, washing machine, dryer, and washer, vacuum cleaner, and dishwasher, and air conditioner. And heating is using gas, so it doesn't cut much load. Air conditioning using electricity consuming load. So those are the few general appliances in every house, most of the houses. So we know the load profile of that because there will be smart meter in the house. So this system operator can easily see the load profile of yours because usually we wake up in the morning, breakfast, we use many people they use a toaster, etc., sandwich maker, etc. Get shower with hot water. The load profile in the morning is slightly up and then goes down, and 5 p.m. onwards goes up slightly. Whereas industrial it will be going up like that, right? So it's challenging, and things have become automated, but still a lot of work going on because it's not a ending story. Things are, the behavior of the consumers are growing, is varying, the nature of loads are different, so it's not talking.
So just a quick follow-up, could you please share that algorithm or any literature for long-term or short-term energy planning based on GNP like you had just shared?
You can easily, I haven't done long-term forecasting, I haven't been very short-term and short-term. For long-term, you can easily go to sciencedirect.com or IEEE Explorer, you can easily download paper. Or if you send me email, I can give you some papers link.
Okay, thank you.
Any other questions?
Just my concern is about grid code. In Nepal, one of the grid code standard. It's in Nepal transmission line less than 4% plus. What is your expected? Another question is about what is the difference between SBDC and DC back to back? Because we get one proposal from China State Grid to connect to integrate between Nepal and China. They said the SBDC is very expensive. We will follow the DC back to back. Because we have in India interconnection is in AC. AC 200 in AC connection we take from China. It is equivalent or not?
And usually the main difference with DC system is, high voltage DC system is, like you might know the history of power system. There was an argument between Westinghouse and Edison, right? One was favoring AC, other was favoring DC. Finally AC won over DC, right? But that doesn't mean that DC is completely out of the system, because we need to transfer large bulk of power, and HVDC system is the potential candidate for that. Do we know that in 1915 in Sweden, I forgot, I think the name of the island is Gotland or something, you can just Google. There was an HPC in 1959 covering around 60 kilometers, I don't know, under the sea. So China is quite, it depends, if you are looking towards Russia or that region, it can be done with AC like with India. It still depends on energy policy matter. Okay? But I, as a energy system planner, smart grid planner, I designed the system. And for the connection, this thing we have to maintain the country standard. I don't have much knowledge about standard here, but we have to maintain the standard. And that standard is not only for Nepal, China has also, they also have to maintain it. Similar with India, right? So I think that should not be a much concern. The concern is whether are you hungry, are you eat or not. The concern is here. The concern is your wallet is full or not. The concern is not how I will go to there and I will sell the thing. No, you have something. You should have the enough capacity. Then only we can think of that. Those HVDC, DC back to back, both things are secondaries. Both things will come later on. The first thing is how to make Nepal's future power be sustainable. How to have energy, sustainable energy future. That is the main concern here. Those are all have some stability issues, transient. Those are, you can easily use any power or any software. You can easily realize. That's the talk today. Any other question?
So you just talk about the cyber security in this part. I just get it. And another question is, we are talking about microgrid, and what will be the challenges or possibilities if you go for an AC/DC hybrid microgrid or DC microgrid within your analysis?
I haven't worked on this part actually, but I was reading one article recently, and I think from IIT Mumbai, I believe, research that they came up with the conclusion, I think, in their case study, not it may happen everywhere. DC was working better than giving least cost compared to AC. And going back to cybersecurity, actually that could be a very different area, and I believe over here today. Like I mentioned in the very beginning, power system is the most complex human-made system in the world, most complex. And the smart communication system is much more challenging, as you were saying. So everything has become algorithm based, all programming, right? Like I can easily control everything my subsystem anywhere in the world. But at the same time, that's a very good news for those cyber threats, cyber attacks, right? So lots of algorithm has been, people are working in that area, how to overcome those issues and create a good firewall and protect our system. Because that's reliability and security. So those two things are very important, not only in power system, everywhere. In our human life also, how reliable is my body and how much security I have, right? Those two important things. So that is the main answer.
Last question is this communication network will be best suited for the smart grid, whether it is the power line communications or wireless communication.
Well, that's a good argument these days, wireless or the
Power line.
The power line. Right now, wireless is not, people are working, but not up to the point of good success, right? But you never know in future, because things are really challenging, because wind power depends on wind speed, solar depends on the radiation, and all of a sudden there can be cloudy weather, there can be rain. And similarly, the behaviors of neighbors are different. My behavior is different from others. And electric vehicles charging, discharging, plugging, unplugging, so several things. So I don't know, wireless, maybe after some time, but right now still we are after power line. Thank you very much.
Power sector basically, NEA का president का नाम आता है ना, तो ये yes, आज को यो प्रेजेन्टेसन स्लाइड तपाईले हाम्रो एरियाको टाइपमा पनि पाउन सक्नुहुन्छ। त्यसैगरी यो प्रोग्राम युट्युबबाट हामी लाइभ स्ट्रिमिङ गर्ने गरेका छौँ। भोलिपर्सि फेरि पनि केही छुटेको छ भने तपाईले त्यो एनइए नेपाल सब्स्क्राइब गर्नुभयो भने त्यहाँबाट तपाईले डिटेल पाउन सक्नुहुन्छ। हामी त्यो कल गरेर बसेर र सबैले यो धन्यवाद दिन चाहन्छु यहाँलाई यहाँ आइदिएर प्रोग्रामको सहभागी हुनुभयो र यहाँदेखि फेरि के आग्रह गर्न चाहन्छु भने यहाँ पनि सधैँ तपाईँ धेरैजना चाहिँ एनइएको मेम्बर भइसक्नु भएको छ। कसैको रिभ्यूबाट बाँकी छ, रिभ्यूबाट पनि बाँकी छ भइदिनु होला। यो एनइए हाम्रो संस्था हो। त्यसै गरी हामी यो साउन्ड 3 मा एनइएले इन्टरनेटले बनाउन गइरहेको छ र यसको क्याटेगोरीहरू हुन्छ। हामीले एक्जिक्युटिभ राख्न धेरै टाइम लाग्यो र विभिन्न विधाहरूमा विभिन्न क्षेत्रमा काम गरेको एक्सपर्टलाई सम्मान गर्ने कार्यक्रम रहेको हुन्छ। त्यसमा चाहिँ आफूलाई ठिक लागेको साथै पनि तपाईँले रेकमेन्ड गर्नुहुन्छ, कमहरू दिएको छ र अब प्रोग्रामको लास्टमा हामीलाई एनइएलाई आर्मीले इन्टरनेट उपलब्ध गराइदिएको धन्यवाद दिन चाहन्छु। साथै यहाँले पनि यहाँको उपस्थितिले नै यो प्रोग्राम सफल हुने हो। आज हरेक फ्राइडे नयाँ लिएर हामी आउँछौँ, सधैँ आइदिनु हो। यति भन्दै यस प्रोग्रामलाई कन्क्लुडिङ रिमार्क्सको लागि एनइएका प्रेसिडेन्ट म पनि यहाँबाट बिदा हुन चाहन्छु। धन्यवाद।
डाक्टर पारस मण्डलजी, नेपाल इन्जिनियर्स एसोसिएसनका तथा नेपाल विद्युत प्राधिकरणका प्रमुख नेपाल इन्जिनियरिङ काउन्सिलका स्टाफले उपस्थित हुनुभएका सम्पूर्ण इन्जिनियर साथीहरू, आज विशेष इम्पोर्टेन्ट टपिक्समा आज लेक्चर हाम्रो अब सिभिल सेक्टरमा बढी हुन्थ्यो, अब यसमा इलेक्ट्रिसिटीको सेक्टरमा, ग्रिडको सेक्टरमा नेपाल जस्तो देश जसले इलेक्ट्रिसिटीमा निकै दुःख भोगिराख्नु परेको छ र यो हाम्रो नेपालको हरेक नागरिकको लागि महत्त्व र प्रशिक्षणको विषय हो। यसबाट भर्खरै पनि फेरि लोड सेडिङ लामो समय रहन्छ भन्दा भन्दै यसबाट लोड सेडिङबाट नेपालीहरूले विशेष गरी काठमाडौँवासीहरूले यसबाट राहत पाएको छ र त्यसमा डिमान्ड साइड पनि त्यहाँ अब विद्युत प्राधिकरणका म्यानेजिङ डाइरेक्टर कुलमानजीले भन्नुहुन्छ त्यो बेसिकली डिमान्ड साइड म्यानेजमेन्टलाई विशेष किसिमले म्यानेज गरेको हुनाले हुनसक्यो भन्नुहुन्थ्यो। आज यो पनि अत्यन्तै महत्त्वपूर्ण विषयमा डिमान्ड साइड म्यानेजमेन्टको र त्यो डिमान्ड र सप्लाईको कुराहरूमा इम्पोर्टेन्ट कुराहरूमा उहाँले प्रस्तुत गर्नुभयो र अनि विभिन्न सोर्सेसहरूलाई ल्याएर सप्लाई गर्ने कुराहरू। पछिल्लो हप्ता दिल्लीमा गएको थियो, त्यो दिन बाई द वे 47 डिग्री परेको थियो, हुन त नेक्स्ट डेदेखि घटेको थियो। अनि त्यहाँ टाइम्स अफ इन्डियामा एउटा न्युज आएको छ, त्यसमा हाइएस्ट इलेक्ट्रिसिटी डिमान्ड भएको दिन 7,003 मेगावाट पत्रिकामा आएको थियो। मैले वास्तवमा फेसबुकमा राखेको थियो त्यो कुरा। त्यसले गर्दाखेरि यो डिमान्ड साइड म्यानेजमेन्ट, इलेक्ट्रिसिटीको ग्रिड, स्मार्ट ग्रिडको कुराहरू अहिले भर्खर नयाँ इनर्जी यो नयाँ कुराहरू आएर हामीले यो हाम्रो कम्युनिटीलाई कन्ट्रिब्युट गर्नको लागि इम्पोर्टेन्ट छ। त्यसमाथि पनि मिक्स सोर्स अफ इनर्जी, अहिले हुन त संसारभरि ग्रिन इनर्जी चाहिन्छ, अन्त नेपाल त्यसरी ग्रिन इनर्जी नै छ सबै, किनभने हामी फर्म पावर विन्ड पावरहरू प्रयोग गर्न गरेको छैन, पहिला सकेर अब गर्नु पनि अब त्यो भएन, किनभने रिन्युएबल इनर्जी ग्रिन इनर्जीमा जानुपर्ने बेलामा र अहिले जस्तो उहाँले देखाउनुभयो अमेरिकामा विन्ड एउटै ठाउँमा जस्तै एउटै जेलको अघि उदाहरण एउटा जेलमा 1 मेगावाटको पावरमा 2.3 मेगावाटको एउटा सिस्टमभित्र, त्यसभित्र सबै खाले सोर्सहरू विन्ड सोलरहरूदेखि लिएर सबै आवश्यकता अनुसार म्यानेज गर्ने। त्यसले गर्दाखेरि यो इलेक्ट्रिसिटी डिमान्ड म्यानेजमेन्ट एकदम च्यालेन्जिङ छ, हाम्रो देशमा त झन् बढी च्यालेन्ज छ र मलाई आशा छ यहाँ उपस्थित हुनुभएको धेरै साथीहरूले यस बारेमा राम्रो डेप्थमा पढ्नु भएको रहेछ भने किनभने उहाँहरूको त्यो जिज्ञासा क्वेसन पनि बडा इम्पोर्टेन्ट उहाँसँग कन्भर्सेसन किसिमको थियो। त्यसले गर्दाखेरि धेरै साथीहरू यसमा हुनुहुन्छ र यसले हाम्रो यो सेक्टरलाई चाहिँ सक्षम बनाउन मद्दत गर्ने नै लागेको छ। अब भर्खर सबैजना साथीहरू नयाँ हुनुहुन्छ, हामीले इन्जिनियर्स एसोसिएसनले हरेक दिन गर्ने फ्राइडे कार्यक्रमहरूमा कतिपय साथीहरू विशेष गरी विदेशमा हुने साथीहरूले हाम्रो कार्यक्रमलाई क्लोजली फलो गरिरहेको भएको छ र उहाँ फिजिकली यहाँ सदस्य हुन सक्नुहुन्न, त्यति मात्र नभएर नेपालमै भएको साथीहरू पनि यो हलमा आउन सक्नुहुन्न। त्यसैले गर्दाखेरि हामीले यो भाया नेटको सपोर्टबाट युट्युबमा लाइभ देखाउने गरेका छौँ। अब अघिल्लो 2 हप्ता 3 हप्ता पहिला हामीले त यही हलमा एउटा कम्पिटिसन ड्रोन बिजनेस कम्पिटिसनको फाइनल कम्पिटिसन पनि गराएको थियो। त्यतिखेर अमेरिका, स्विजरल्यान्ड र हामीले यो हलबाट 3 ठाउँबाट सँगै इन्टरेक्टिभ टिमको त्यहाँको जजहरूले जजहरू तुरुन्तै हामीले आधा घन्टाभित्र त्यो सबै रिजल्ट निकालेर यहाँ 7.5 लाख रुपियाँ पनि यसरी टेक्नोलोजीले विकास गरिराखेको छ र साथीहरू नयाँ इन्जिनियरहरू यसमा अगाडि आइराख्नु भएको छ। म सबैलाई शुभकामना दिन चाहन्छु। अनि यो नेक्स्ट विकमा फेरि इन्टरनेसनल वुमेन इन इन्जिनियरिङ डे भनेर यही कार्यक्रम हुँदैछ। फ्राइडे टक सिरिजमा अलिकति कार्यक्रम हुँदैछ। अब ब्रिटिस राजदूत पनि आउनुहुन्छ, आधा घन्टाको पछि होल डे 11 बजीदेखि 5 बजीसम्म एक्जिबिसनको कार्यक्रम छ। सबै साथीहरू होला ओपन टु र अब अघि भर्खर भूषण साथीले भनिहाल्नुभयो, हाम्रो सानो दिनमा 2 हामी देशले हामी मनाउँछौँ। त्यसमा 31 गतेदेखि नै कार्यक्रम छ, असारको 31 गतेदेखि नै। त्यसमा सबै साथीहरूले सहभागी हुन अनुरोध गर्दछु र आज यहाँ दिनुभएको आयोजन भयो यहाँको टकहरू सुनिदिनु भयो यसको लागि सबैलाई धन्यवाद। आज यो कार्यक्रम यो टक प्रोग्राम यही अन्तर्गत जानकारी गराउँछु।
पैसा माग्ने हो पुगेको छैन हामीलाई त्यसलाई पुग्दा त पुगेको मान्छे
First, second,